Welcome to Math today. We are looking at a review of Unit 2, Univariate data. We're doing a review for the semester final, which we'll be doing later this week. So today's objective is, given a set of data, I can calculate the mean, median, mode, and standard deviation, and interpret histograms correctly in 3 out of 3 problems. So those are all the topics we covered, or most of the topics we covered in Univariate data. Mean, median, mode, and standard deviation, as well as histograms, bar charts, dot plots. So think about which of these emojis best represents you. So first we looked at mean, median, and mode, which we described as centers, or measures of center. How we determine the measure of the center of a set of data. So first let's calculate the mean. Do we remember what mean, median, and mode all are? So mean, which we also know as average, is when we add all the numbers together and divide by the count of them. You can see over here we have a little summary. That was the mean. The median is when we find the middle number, and the mode is the most common number. So in this case, we have a question that says, this data set shows the number of hours several students spent on homework in a week. What is the mean of this data set? So to do a data set, we're going to do the mean, we're going to add these numbers together on top. Remember, 0 is a valid data point. It does count as one, so we include it. And then we count these. 1, 2, 3, 4, 5, 6. There are 6 data points, so we put that on the bottom. If we put all of these into our calculator, let's see, I have 9, 17, 20, looks like 27 on the top, and 6 on the bottom. We put that in our calculator, we get 4.5. So the mean of this data set is 4.5. So now we have another one, a stem and leaf plot this time, and we're asking what is the median of this data set. So you can remember stem and leaf plots. For the stem, this was going to be the tens place, and the leaf is going to be the digits place. So this number represented 16, this one is 18, this one is another 18, this one's 22, 27, and so on, 30, 34, another 34, and 35. So to find the median, we're talking about the middle, right? Line them up, choose the middle number. And we have this process where we can cross out the first number and the last number. And we should get to the middle after we've crossed out all the other numbers. You can see we only have one number left now. We did first and last, until we got to one number left, and that number has to be the median. 27 is the median in this case. So you give this one a try. See if you can remember how to calculate the median on a stem and leaf plot. This one has quite a few more numbers than the one we just looked at. So we can go through that same process, cross out the first and the last, first and the last, first and last, first and last, first and last, first and last. And you can see in this case, we actually end up with 2 numbers in the middle. So when we have an even data set, we have an even number of data points, we have to find the number that's in the middle of these 2. So in order to do that, we have this method of adding them together and dividing by 2. 25 plus 26 is 51. Divide that by 2, we get 25.5. 25.5 is the median here. Another way you can think of this is what number is right in the middle of 25 and 26? Well, that's 25 and a half. It also asks how many data points are in this set. We just count those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 data points. And that is consistent with what we saw, right? We saw that there was an even number, so we got 2 numbers in the middle. So we expected there to be an even number of data points. So once again, how do you calculate the mean? The mean is sum over the count. The median was the middle number, and the mode is the most common number, or the most common value at least. It might not be a number. So those were our measures of center. Let's take a look at measure of spread now. Standard deviation, how spread out is the data? Now remember, we had a method for calculating standard deviation. We're going to ignore that for just a second. We're going to look at some charts. Remember, we're talking about a normal curve here, like a normal bell curve, when we're looking at standard deviation, something like that. And you can see here we have several different standard deviations shown. And what do you notice is different about these charts? These histograms. Well, the larger a standard deviation is, the more spread out the data is left to right. And then it gets shorter as well. So it gets wider and shorter as the standard deviation gets bigger. How does that make sense if we think about that conceptually? Well, standard deviation is a measure of spread. It's a measure of how far away the data points typically are from the mean. So if standard deviation measures spread, then we can expect as it goes up, it gets more spread out, right? So a larger standard deviation means it's more spread out. A smaller standard deviation means it's more compressed together. The data points are more compressed. They are closer to the mean. So which distribution has a smaller standard deviation here? Be sure to pay attention to the question. Which one has a smaller standard deviation? Well, smaller standard deviation means less spread out. So this one's going to be B, because you can see A is more spread out, and B is only spread out to about there. B is less spread out, so it has a smaller standard deviation. Now, we also had a way to calculate the standard deviation. And remember, we did this by hand a couple of times and then said, that's really annoying, let's never do that ever again, right? So, we have a website. Let me type this in really quick. Let me grab it. We have a website where we can calculate the standard deviation, and there are a lot of these. We maybe give you a couple of different links, and you can also do it in Excel. There was a way we had in Excel a formula that said equals stddev dot p. Remember, the p is for population, and then we put in our range of our data. So you can calculate it in Excel if that's easier for you. So I'm over here in this website, and I'm just going to type these in really quick off screen so I can see both of these screens at the same time. I'll bring that over here. So here's our website, and I typed in my values. I typed in my values from that stem leaf plot, and I just separated them with a comma. You see here we've selected population. We don't want the sample, we want a population standard deviation. And if I scroll down here, it shows us the standard deviation in this blue box. It actually walks us through how to calculate the standard deviation, but we're not going to worry too much about that. We're just going to look at the standard deviation and try to interpret it a little bit. So this is a 12.4 standard deviation. 12.4. So that tells us that the data is typically about 12.4 away from the mean. So we can calculate the standard deviation using technology. Here's another problem. Calculate the standard deviation. So open up that website and give it a try. Try calculating the standard deviation on one or both of these data sets. And I will do the same right now. Type these in really fast. All right, so that first one, oh, did I type that in right? 72, 74, 77, 85, 87, 92, 96, 97, 98, 105, 110, 112. I get a standard deviation of 12.9 if I round it. 12.88706, which I just round to 12.9. All right, how about this second one? What do we get here? 72, 73, 77, 82, 83, 84, 85. Notice that both of these data sets, or actually just this one, but this data set has repeat numbers, 77 twice, 85 twice. That's totally valid. You can have the same data point more than once. So let's see. My standard deviation I get on this one is 5.6 if I round it. So you can see this standard deviation is much larger than this one. This one has a smaller standard deviation. So what does that tell us about this data set? A larger standard deviation tells us that the values are more spread out. The values are less spread out down here. And we can confirm that 72 to 90 is not as spread out as 72 to 112, right? So which of these triathlons do you think is harder? Do you think one is harder than the other? And can you tell based on the standard deviation? Well, we determined that the first one, the first triathlon, had a larger standard deviation. Why might times be more spread out? So if we go back and look at these, say these are times for the triathlon, this one looks like it had much higher times. So these ones were all kind of clumped together, and this one had more people finishing in longer time. So maybe it would make sense to say that this one was a harder course, so that the people who weren't quite as, who hadn't trained quite as hard or who weren't quite as fit or had trouble with certain parts of the course, that didn't have as big an effect on this one, probably because there wasn't as much challenge to it. So maybe the first one was harder, it was a more difficult course. So we had a problem like this on one of our quizzes, where we're comparing the mean and the standard deviation of two different cities. Here's the cost of homes in two different cities, two different neighborhoods. And we have a mean over here on City 1 is $302,000, and City 2 it's about $298,500. Now, those are, not the exact same number, but based on the scale, they are very close to each other. We'd say those are almost equal. But the standard deviation is actually pretty different. 20 and 34.6 are pretty different standard deviations. So City 2 standard deviation is much higher. So if our mean is about the same, but our standard deviation is higher in City 2, which one of these answers down here is accurate? What would we conclude about this data set? There we go. Well, if the means are about the same, that means that's our measure of center, right? That's our typical value. So our typical cost of our homes are about the same. So this one says, the homes in City 1 cost more than the homes in City 2. Well, the cost was just our typical value, right? We said those are about the same, so it's not that one. The homes in City 1 cost less than the homes in City 2. Yes, it's just the cost again. That is not different. We said the cost, the typical cost is about the same. So now we say the costs of homes in City 1 vary more or they vary less. Those are the two options we have left. So does City 1 vary more or less than City 2? The standard deviation is smaller, which tells us that the costs vary less in City 1. So that is our answer. The costs of homes in City 1 vary less than those in City 2. Okay, so that's everything on standard deviation. And now we will take a look at histograms and, and some other kinds of charts. So we started off with dot plots. Remember, when we look at charts, the whole purpose of charts is to make understanding data easier. That's the whole reason we make charts. So this dot plot shows the number of each type of cookie sold at a bake sale. What was the second most popular cookie? Well, this is clearly chocolate chip because that's the second tallest bar, right? This is the most popular, it's the tallest bar. Chocolate chip is the second most popular, it's the second tallest bar. We also had bar charts that look like dot plots, only they have bars and a scale on the side. But these are still counts. In this chart, the employees at a store were asked what transportation they used to get to work. The results are shown in this graph. How many employees bike to work? Well, we look at the bike column. You see it comes up to 3. We read 3. 3 employees bike to work. We also had stem and leaf plots. We've looked at those already a little bit today. This stem and leaf plot shows test scores of several students in an ELA class. So remember, these are 54, 57, 66, and so on. How many students scored above a 75? Well, 75 would be right about here. So we just need to count the ones above 75. So there's 1, 2, 3, 4. So there were 4 students that scored above 75. Extra challenging question, what percentage of students scored above 75? So this is the same data set. We still have 4 students that scored above 75. How do we calculate the percentage? Well, percent is the number of interest, or the number in question, over the total number. So we already have the number of interest. We know that's 4. 4 on the top. Now we just need the total number on the bottom. So we count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 total data points. So if we reduce this, that'll be 1/3, which is 33.3%. We also looked at histograms. So remember, a histogram is a lot like a bar chart, but now we have intervals down here. We have a range of numbers instead of categories. So instead of chocolate chip, we now have a class size of 1 to 5, or a class size of 6 to 10. Any class that's between those numbers will get counted in this bar. So this histogram shows the distribution of class sizes at an elementary school. How many classes had 16 to 20 students? We'll go to the 16 to 20 bin and look at how many were counted. So there were 5, and that's our answer. 5 classes had 16 to 20 students. This is the same histogram we just looked at, but now we're asking how many classes have less than 16 students or have fewer than 16 students. So 16, that cutoff is right here. So that tells us we should draw a little dotted line right there. We're asking less than 16 students, so everything below that dotted line. So this first column has 2. The second column also has 2. And this third one has 1. So then we just add those together. 2 plus 2 plus 1 equals 5. So 5 classes have fewer than 16 students. Let's take a look at one more histogram. This histogram shows the number of hours volunteers worked in a day at a museum. How many volunteers worked at least 5 hours? So there's one of those key terms again, at least. So we're going to find the 5. 5 is right there. So we know that our cutoff is right here, right at the 5. And at least 5 hours means 5 or more. 5 or more hours goes this way. So we need to calculate how many were counted in these two bars. Well, in this one, looks like it's right at the it's right at the 4 level. So there are 4 in that bar. And this one is between these two bars. So if we come over here and look at what these two lines are, there's 6 here and 8 here, and it's between those two, so it must be 7. Remember, we're counting whole objects here, so this is going to need to be an integer. So we're going to take 7 plus 4, or 4 plus 7, and we'll get 11 volunteers worked at least 5 hours. So that's it for everything in univariate data. It's down here. Given a set of data, I can calculate the mean, median, mode, and standard deviation and interpret histograms correctly in 3 out of 3 problems. Get them all right. With these emojis, think which one best represents you on that objective.